In this video, we'll take a look at eigenvalues and eigenvectors. The problem is to find a basis for each eigenspace of the matrix A. Well, the general procedure to find eigenvalues, we'll take the determinant of the matrix A minus lambda I, and we will set that equal to 0. I'm just going to scribble a little bit on the right side here. So let's remember, we should be imagining that the identity matrix, 2 by 2 identity matrix, looks like this. And as we build the matrix A minus lambda I, we're really taking our matrix A and effectively just subtracting lambda off those diagonal entries. So it's nice to be able to visualize that quickly, that our matrix is going to look like negative lambda, 3, 3, negative lambda, just subtracting lambda off the diagonal entries. So coming back to our calculation here, we're going to take the determinant of the matrix negative lambda, 3, 3, negative lambda, and set that equal to 0. We'll calculate this 2 by 2 determinant in the usual way, just multiplying the entries along the main diagonal. That gives us lambda squared, and subtracting off the product of the off-diagonal entries, so that's going to be minus 9, and that's equal to 0. Typically, we're going to be factoring to solve this equation, so we'll factor this as lambda minus 3 times lambda plus 3 is equal to 0, and that gives us our lambda values 3 and negative 3. So these are the eigenvalues for the matrix A. Now that we've found our eigenvalues, let's take a look at the eigenspace corresponding to lambda equals 3. The shorthand notation for that would just be E3. So the general procedure for finding such an eigenspace is to solve a system of equations, and the system you want to solve has coefficient matrix A minus lambda I, and it is a homogeneous system, meaning our constants on the right side here are all equal to 0. Since we're looking at the eigenspace corresponding to lambda equal 3, we're going to actually sub in that value of lambda here. Our coefficient matrix in this particular part of the problem will be A minus 3I, and again that's a homogeneous system. So if we subtract 3 off the diagonal entries of our original matrix A here, we're going to end up with the following coefficient matrix, and we're now going to solve this homogeneous system. So we can do some Ghostwritten elimination here. Let's take row 1 and divide it by negative 3. So we've now got a 1 in the upper left-hand corner. And if we now eliminate this entry in the bottom left-hand corner here, if we do row 2 minus 3 times row 1, we're going to get a 0 row in the bottom, and top row stays the same. So we've now got this matrix down to our REF, and we're going to be able to solve the system. What we're solving for here are the eigenvectors of this matrix. Typically we call our eigenvectors x, so it makes sense to call these variables here x1 and x2. We've got a leading 1 in the first column there. Second column does not have any leading 1s in it, so x2 is going to get a parameter. Let's say x2 is equal to t. Top row tells us that x1 minus x2 is equal to 0. In other words, x1 is equal to x2. In other words, x1 equals t. So if we write up our vector x in vector form, both of our components are equal to t, and we could write that a little bit more concisely as x equals 1, 1 times t. So we could say x, the eigenvectors here, could be any multiple of the vector 1, 1. Technically, in order for it to be an eigenvector, we would need a non-zero multiple. The 0 vector is not technically an eigenvector for this matrix. Now the problem was asking us to find a basis for each eigenspace. So to finish off this part of the problem, we could say the basis will be the vector 1, 1. It would also be correct to take any non-zero multiple of this vector for your basis. So if you got 2, 2 or 3, 3, those would be correct answers. So I've just copied our original matrix A from the previous screen, and I've copied our answer from the previous screen. We found the basis for the eigenspace E3 was the vector 1, 1, where any non-zero multiple of that would also be correct. Now just to make sure we have a clear understanding of eigenvectors and eigenvalues, let's do a little check here, make sure this is correct. The idea is that if we take our matrix A and we multiply it by this eigenvector here, 1, 1, we should end up with a multiple of this original vector that we started with. So if we do our multiplication, we get the vector 3, 3. And what we're really noticing here is that when we take our original matrix A and multiply it by 1, 1, we're getting 3 times that original vector 1, 1. So we say 1, 1 is an eigenvector for A, and it's corresponding to the eigenvalue, the number 3. Now the problem asked us to find a basis for each eigenspace of the matrix, so we'll now need to look at the second eigenspace, E negative 3. Remember, the general procedure is to solve the system A minus lambda I, and that is a homogeneous system, meaning our constants are all 0. In this particular case, our lambda value is negative 3, so we're really looking at the matrix A plus 3i and going and solving that homogeneous system. So if we take our matrix and we add 3's along the main diagonal, we end up with this coefficient matrix here. And we'll go ahead and put this into our REF. So let's take row 1 and divide by 3. Next, we can take row 2 minus 3 times row 1, and there we have our REF. Now what we're solving for here are the eigenvectors of the matrix A. Those eigenvectors are usually called x, so it makes sense to call these variables x1 and x2. We've got a leading one in the first column, but we don't have a leading one in the second column, so x2 is going to take a parameter. And our top row tells us that x1 plus x2 is equal to 0, meaning x1 is equal to negative x2, or in other words, x1 is equal to negative t. So the vector x that we're looking for looks like negative t, or if we write that a little bit more concisely, negative 1, 1 times t would be another way of expressing x. So any non-zero multiple of the vector negative 1, 1 is an eigenvector for the matrix A. Technically, the 0 vector is not an eigenvector, so we need a non-zero value of t here. Quickest way of describing this is just to write down a basis for our eigenspace. So we could say a basis for our eigenspace corresponding to lambda equal negative 3 will be the vector negative 1, 1. And it would also be correct to use any non-zero multiple of this vector. So when the first component is negative, it's actually a little bit more common to multiply through by that negative 1 and actually express it as 1, negative 1. So this, I would say, would be the more typical answer.